once, twice. Okay. So last class, we talked about, linear regression, and we are trying to find, again, in some sense, a line, a linear equation, in terms of the number of variables that best fits the points. That's what linear regression is. And we saw that there was an algebraic way to compute the linear, the coefficients of the linear regression, and that was kind of amazingly concise, and in principle gave us a way to compute, to find the optimal coefficients of the coefficients of the best fitting line using basically a matrix inversion and a couple of matrix multiplications. I don't remember what the exact equation is, but it's something like, I should probably know this. Does anyone want to help me here? What is the formula? The coefficients are equal to, I think, is it AT times A? Okay, let me look from last time just to double check that. Sorry. Right, it's AT times A inverted times ATB. Okay, so there is an equation, an algebraic way to figure out what were the optimal coefficients of the line given our data matrix and given our y values, our target values. The bad things with this method, so we could in principle just reduce our problems of linear, finding solutions to linear regressions to evaluating this equation. There tend to be two problems for it. One, finding the inverse of a big matrix. This is if you have an n by n matrix that you're inverting, that's an n cubed operation if it's not a sparse system. So doing an inversion is an expensive thing. The other thing about it is that this formulation in terms of matrix products is a little bit brittle. It's hard to extend it to other optimization criteria. Okay, so maybe we want the best fitting line with some other properties to it. Okay, and so there is another approach to solving linear regression problems that is kind of the foundation of most learning sort of machine learning technologies these days. Things like deep learning, are very much based on kind of gradient descent search kind of approaches. And I'd like to kind of talk about that, this kind of model as a way of better understanding how these techniques work, and then generalize linear regression in certain ways that it becomes, gets better solutions in certain ways than just fitting the points as well. Okay, so what is the idea of using a kind of a gradient descent search type of approach? There's a way to view what you call linear regression as if it's a parameter fitting problem. So let's imagine that we are dealing with, again, a line in 2 dimensions. There is a y value, there is one x value, one variable. The best fitting line, the regression line, is going to have a slope and it's going to have a intercept. Okay, and that's what defines it. Now, the slope and the intercept, those are 2 parameters that define what the best fitting line is. Okay. Now, let's say that we're going to try to search all possible values of W0 and W1, okay, and evaluate how well they do. Well, our goal is to minimize least squared error, okay? So we know that for every one of our training examples, we're assuming we're given n training examples. Each one of them has an x and an associated y. The error for a particular value of intercept and slope, the average error, okay, is going to be something like 1 over n times the sum of the error on each point. We're trying to minimize sum of squared errors. So this was the actual value. F of xi is the prediction, okay, where f of xi is going to be simply this equation. So it's f of xi is basically w naught plus w1x, w1 times x, which in this case the ith value of x, the ith training example. And we're squaring it. This is the residual, okay? The square, this is the residual. We want to minimize the sum of squared error. For any given w naught and w1, this equation is going to give you the sum of squared error, okay? And our goal here is going to be to try to find what are the w naught and w1s that achieve this minimum. Any questions about that? Okay. Does everybody see that if we're trying to find, this is exactly the statement of the least squares of the fitting. We seek to find the values of W1, W0, and W1 that minimize this, where this is the sum of squared errors for that line. Okay. Okay, question is, why are we dividing by 2 to the n? That is a good question. If we want to figure out what the sum of squared error is, we would not divide by the 2n, right? Now, the first thing I'll say is, if we're trying to minimize the sum of squared error, it doesn't matter why we're dividing, whether we divide by 2n. Does everybody see that for any w, no matter what w1 or w2, if we divide the least squared error by the equivalent of a constant, okay, the point that used to minimize it doesn't minimize. The point that used to minimize it, okay, still minimizes it. Okay, so from a point of view of why doesn't it matter that we're dividing it by 1 over 2 to the n? That's the important point. If we're looking to find what are the parameter setting that will minimize this term, dividing it by a constant doesn't change that. Okay, we will still, if we find the solution to this equation, the error, to find the parameters that minimize this error, the notion of error, it would be the exact same parameters that would minimize it if we didn't have this 1 over n term. That said, why do we have a 1 over 2n term? And the reason is that turns out to be, it's kind of for algebraic convenience a little later on. Okay, we're going to be taking derivatives of this thing. And when you take the derivative of this thing, the 2 term from here is going to go down, and it's going to cancel it. And the fact that this thing is summed up over n when we're taking the derivative of it, that will essentially also create an n times something, and that will also get canceled. So basically, we have this constant here just because it'll look good when we make derivatives a little simpler later on. Okay? That you may not believe, but what you should believe is that that if we minimize this expression, we are going to minimize exactly the least squared error. Any questions about that? Okay. So what is the interesting thing? It turns out that this error function here is a convex function. What does a convex function? Well, actually, let's plot it. Okay, here I'm showing you, assuming that, let's just make this a one-dimensional thing. So instead of trying to fit the line, y equals W1 plus W2x, which is W0 plus W1x. Let's say that we already know that W naught is 0. Now we have one parameter. We can now think for any given example here. Here is a set of training examples, which are a bunch of x, y points. If we know that W naught is, the intercept is going to be 0, we can now ask ourselves, what is the error as a function of the slope? Okay, I can have this, once we fix the intercept, the only parameter of our regression line is going to be the slope. This here, okay, is a plot of what is the error, okay, for this point set as a function of the the slope. And if you look at that, if you understand what this is, you look at that, you will see a minima, and that minima looks like it's very much at a slope of about 1. Okay, you will see that when you raise the slope, okay, to be something bigger than 1, the sum of squared error increases. When you lower it, the sum of squared error decreases to a point and then goes up again. The shape of the error function is going to look like this, okay? And this is a convex function, okay? Convex functions are very, you studied them when you took calculus. Convex functions have a lot of interesting properties to them. One of which that is good, the most important one for our purposes, that there is a single, okay, local minima in this function, which means that the local minima is the global minima. So if we were, let's say, wanted to find out what is the slope that what is the slope that minimizes the error for this data set, we could try from one point, okay, one value, guess a value for the slope of the line. If we then figure out what the tangent is at this line, if we could figure out which direction is it that will go down on this error function, we could now come up with a new point to try and evaluate the error function. The hope would be that if we keep going in the right direction, okay, first of all, if this is a convex function, there always is a direction to go in, which will lower the value of the objective function until you get to the minima, okay? And so long as we can find that direction, which turns out to be easy, okay, this gives us a procedure to tell us which direction do we walk to get a better value of this, okay? And in one dimension, that should be pretty convincing. This is what the surface looks like in 2 dimensions. Now here we have an intercept parameter, we have a slope parameter, and the y value is the error as a function of both the slope and the intercept. Every point on the xy plane here defines a line that could fit those points. The y value represents the the error in fitting those points. If you look at this curve is now, it's not like just a parabola. Now it looks like a bowl, but the same phenomena holds. From every point that's not the global minima, there is a point, a direction where if you go in that direction, it will get lower, okay? And this gives an argument that we should be able to walk down this surface and eventually find the minimum one. Any questions about that? The critical thing here is to see what we have done. We took as input a set of points. Based on the points, we have an error function, which I might as well go back to the full-blown error function here. We can evaluate that error function for any parameters, possible choice of parameters for the line. Once we have that, we get a surface. Because this surface happens to be convex, okay, it is kind of a smooth, a bowl-shaped thing. We can kind of use some kind of a constantly walking downhill thing to get to what is the optimal parameter. Any questions about that? Okay, so gradient descent search is the kind of the name that we're trying to deal with, of this procedure that we're going to use. The input is, again, we have a function with the property that it has only one global minima, okay? That's convex. If we want to find what that minima is, we have to find a direction and just walk down, okay? And so the key question here is to try to find a direction from our current point in parameter space where it will make for a better fit, okay? And there is a property that you learned when you took calculus, okay? The fastest direction down is going to be determined by the slope, okay, or the tangent line at the current point. So if we can find the slope of the tangent line at the our current solution, that will define what direction gives us our steepest descent down. And that's, if we want to try to find our minima quickly, the best thing to do is to go in the steepest manner first. Any questions about that? So how do we find, if we're starting out at a particular point, okay, B, let's call it B, okay, how could we find what was the slope at a given point here, the tangent line? In one dimension, okay, which is the way I'm used to thinking about this, okay, we know that a line is defined by 2 points. If we took a very much a nearby point to it, if this point here had coordinates x, y, if we take a look at a point x plus delta x plus y times y delta x, okay? Actually, this looks, okay. If we take a look at you know, basically a point that is, I see, y is whatever the function is, okay? We want basically a point that is slightly offset from this. Once we know what delta x is, okay, we could now compute what is the value of y here. Once we have that, we now have 2 points. We could fit this with a line. The slope of that line will tell us whether we are going up or down. And so in you know, if we have a curve in 2 dimensions, if we start out with a point here, if we go delta x in this direction, okay, it would be leading us down. If we went delta x in this direction, the slope would be minus, meaning that that would have been the wrong way. And so the real way we would make progress is here. So in principle, if we want to find the point going down from a given point, one way to do it would be, at least simplest way would be, take our given point, sample the neighborhood around our x. For each one of these, compute what f of x is, what y is, okay? And then take the x, move in the direction that would lead us down the most, okay? So if we didn't know any calculus and we wanted to do this kind of a approximation, we could conceivably do it by sampling. take X, take some points right around it in the very close local neighborhood, compute what the value of what the error function is in all of these points. If it's convex, one of them, his direction should be down, and we take the direction that is down the most. Okay? Any questions about that? Okay, so this much I understand without doing any calculus. That said, okay, if you remember back to when you took calculus, okay, the way that you find what the slope is at a particular point is by taking a derivative. And in higher dimensions, you do it by taking partial derivatives, okay? So the gradient at a given point, which way do we go down, okay, requires computing the partial derivative of the objective function. What was our objective function before? Okay, our objective function was here. Okay, when we write f of x over here, really what we've got is an objective function that would look something like, you know, if 1 over 2n times the sum as I goes from 1 to n of yi, okay, which is here is what I'm going to call b, okay, and what I do for now, okay, yi minus w naught plus w1x squared. This was my original error function, okay? Now, again, I am summing up over all n examples, okay? This was the y value that I'm trying to predict. This was my model when I evaluate it from a function of xi. And I am curious to find what is the error as a function of my two parameters, w0 and w1, okay? Now, in this particular example, what is the partial derivatives of this? I am, in this model, okay, because I want to use Mathematica, w is going to be the intercept, and s is going to be the slope, and b is going to be the y value. I want to now know, if I had only one point, what would be the derivative of this function with respect to w, the slope? Okay, well, I'm going to take the derivative of this and taking the derivative of this thing, the exponent. Remember, if you remember that what you do, you lower the exponent by 1 when you take a derivative and you multiply it by that. That cancels out the 2, which was part of your earlier thing. If we took the partial derivative of this with respect to w, this was the partial derivative. If we took the partial derivative with respect to x, with s was the slope, okay? It's a little more complicated because s is being multiplied by x. So we get this on the outside. But bottom line is that when you take the derivatives with respect to your partial derivatives with your parameters, you're basically knowing as you change w, a little change to w, how does that affect, okay, what the error is going to be, okay? And once we have the derivatives, this will tell us what the direction is to go towards the minimum. Any questions? So what is the algorithm for gradient descent search? Okay, basically, we're going to start at some arbitrary set of parameters. Okay, you can start wherever you want. Okay, w, you know, initialize w. Initialize here they call sigma. The parameters here are the theta parameters. Then what are we going to do? Okay, we are going to take in each iteration, we are going to, update each of the parameters, one after the other. In the case of our line, the line has two parameters, okay, theta 1 and theta 0. Okay, what are we going to do? We're going to update the slope. The new slope is the new slope of the fitting line is going to be the old slope of the fitting line minus, okay, this is the derivative of the error term with respect to that that parameter tells us what is the direction in which we will go fastest, or how far will we move for a change in as we add a unit change in x, how much a unit change in sigma j, how much do we change the error? The sign of this will tell us whether we should be increasing or decreasing that parameter. And the value of this derivative will tell us kind of how fast should we change this, how fast will we change these things, okay? In terms of, how will give us kind of a question of how flat is it in that direction. As we change this parameter a little, okay, in some direction, is it going to cause a big change in the error term or a little change in the error term? So this gives us a direction and a magnitude to go in. We're going to multiply this by some parameter alpha, which is going to be our step size. And so basically, we're going to change each value of our parameter by alpha. We're going to add or subtract alpha times a function of how steep the surface is here, okay? And this will give us a new value of the parameter. So what is gradient descent search? We start at an initial point in parameter space. We then look at the partial derivatives around this point. In each dimension, we will know which direction will lead us down towards the minima, and some idea of how important this direction is towards getting to the minima. And we will then take a step of size alpha times the magnitude there in the right direction, okay? And if we're always moving in the right direction, and if the thing is convex, then we will eventually reach the minima. Any questions about that? Okay. Why do we use J as the name of the error function? In the book that I read when I was reviewing this thing, they used J as the error, as the value for the error. Okay, so I don't know of any deeper reason than that. Okay, any questions? Okay, but the principle here should be pretty clear, so long as you accept the calculus right about what these derivatives mean. Okay, and again, if the function is convex, then it should make clear that always walking down gets you to the global minima. And how do you tell which functions are convex? This requires remembering your calculus to in ways that are beyond the scope of what I want to talk about. But basically, you remember that to get a minima, the first derivative of it is remember there was a close connection when you took calculus between derivatives and minima. Okay, how did you find the minima? You took the derivative and you and you tested whether or not it was zero by the analysis of derivatives and second derivatives of functions. Okay, people in the know can tell whether or not a function is convex. If someone tells you a function is convex, I would believe it. If you run your gradient descent search on a convex function, you know you're going to find the optimal point. If you run it on a function which is not optimum, all is not necessary, when the function is not convex, all is not necessarily lost. What happens if you start at this point and you do a gradient descent search? You would look around in the local neighborhood, and this is going down, this is going down, this is going down. Here there is no direction, the derivative is 0. You would report this as a solution. If the function, your error function is not convex, okay, you don't necessarily end up with the parameters that best fit the minimize error. But that doesn't mean you don't get errors that don't do a pretty good job. Okay, when in deep learning, there is a lot of, the functions that people are trying to parameter space when they try to optimize this thing. That thing is not convex. Okay, does that mean they can't use gradient descent search? The answer is no. But it means that they aren't guaranteed the absolute optimum minimum. But there are various tricks that you can use to try to find something that's a better minima. Okay, knowing your error function is convex means you know that you get the optimum. Even if you don't know that, this isn't necessarily a bad thing to do. Any questions? Okay. Okay. Okay, let me move on here. Okay, and this is basically what I was trying to say, that if you have a surface that is not convex, okay, trying to constantly go down, you might very well get trapped in a local optima rather than a global optima. That's unfortunate, but even the local optima is presumably better than your random starting point. If you try this thing from several different places, maybe maybe the local optima that you find, okay, one of them will be the global optima. Okay, fair enough. So if we look at this gradient descent search algorithm again, okay, the slope, the direction that we're going on, okay, is a function of the error function, is determined by the derivative of the error function. This is in some sense well defined. What we're going to do, it's going to tell us a direction that we should, given that we're at this point, what direction should we walk in order to go towards an optima? This value alpha is a step size that tells us how far we should walk. Okay, what that value of that alpha is, okay, is not a priori one alpha being better than another. It should be clear that if we are at a point here and our step size is very, very small, okay, even if we're always walking in the right direction, okay, it's going to take us a long time to get to an optimum. Okay, everybody kind of see that? Okay, so if you have too small a step size, that is bad from a point of view of efficiency. If you have too big a step size, you can overshoot your goal when you get near it. What if when I start over to here, I say okay, I want to walk in this direction, and I want to walk, my X that I'm going to use is over to here, okay? In this case, when I walked over here, I actually passed what was the global optimum, okay? Since, in fact, the new point is still lower than the first point, okay, then I happen to still be making progress. But there is no reason why, if I start at some point and I take too big a step in the other direction, at some point I'm going to be moving, I might very well get a worse solution than I had before. Okay? The idea of walking towards the goal always makes progress so long as I don't overshoot it. Okay? And it should be clear that too small a learning rate, people usually call that constant alpha the learning rate, Okay, people, too small a thing takes long to converge. Too big a thing overshoots the goal. Any questions about that? And it should also be clear that if the region you're in is extremely flat, okay, all kinds of it's very hard to tell whether in a flat region, which direction is it that you really go in, just if you have numerical precision issues, okay? So this becomes a, so this becomes a problem if your step size is too big for overshooting. And in general, this kind of walking rate becomes problem if the flatter your error surface is, okay, the harder it is to move forward there. Okay, any questions? Okay, good. So how do you find what the right value of that learning rate parameter is? Okay, I would argue that there are different ways you could, different kind of algorithms that set that learning parameter. Okay, one of them, kind of the basic idea behind them, basically monitors the progress towards the goal. If you are, not lowering the value of the error very much, okay, after a certain number of iterations, that might be an argument that you multiply the learning rate by some constant, let's say 3, okay, or you give up, okay? If, on the other hand, the error rate has ever gets larger, that meant that you not only overshot the thing, but you overshot the thing by enough that you're now making your solution now is worse than before. If so, that's a sign your step size is too large. Maybe divide it by a factor of 3. Okay. And bottom line, there are library algorithms, optimization algorithms for doing these kinds of things. Okay. But basically, it's probably good in practice not to take the learning rate as constant, but it should be large when you're far from the goal and probably small when you get close to the goal. Any questions? Now, what is the running time of this algorithm? Okay, this is actually an interesting question. What is the running time of gradient descent search? Okay, it seems that you've got what are the parameters that this would actually have? Okay, there are, I'll say, n examples, each of which, let's say, is in d dimensions. And you've got, what you call it, and let's say that we're going to end up running I iterations. What is the running time of this algorithm? Okay. It's I times the cost of executing this statement. How many times are we going to execute this statement? What is the running time of executing this statement? Well, first, this thing is going to depend on, we're going to do this separately for each dimension. So really, there's an implicit loop that's going around d times there. My question is, how much time does it take to evaluate the derivative of, of the error function at a given point? Anybody have an idea? This is what the error function is. Okay. If we take the derivative of this, what is the time that it should take to evaluate, okay, this derivative? Okay. The derivative, if you look at it, well, in here, evaluating what you call it, what the here is our line. Again, the right way to think of it, in here, the cost of this is going to be basically for each given point, it's going to be constant to compute what the prediction from the current parameter is, subtract that from the original, from the target value for that particular point, square it. All this should take constant time to evaluate the square residual at any point. But we have to do this for every single point. Evaluating the derivative here is going to take something like n times the number of dimensions, okay, to evaluate what the local derivative is, okay? Any questions about that? It is clear that, right, as people are saying, the running time for taking the derivative is order the number of examples. And so although this looks pretty fast, computing what that slope is, okay, is an expensive thing. So how do we make that faster? There is the idea of what people call stochastic gradient descent search, okay? Evaluating the time, the partial derivative of the full error equation will take time proportional to the number of examples that we had, okay? What we're looking for is an estimate from all we want from this derivative is an estimate of which way is down, and ideally which is the fastest way down. If instead of using all the points to do the estimate, what if we take a random sample of the points and use that random sample as a to give us a idea of which direction is down. If instead of using n points, we use 64 points taken randomly, okay? Though that probably gives us a pretty good estimate of where, assuming those points are representative, it gives us a pretty good representative of what what direction is down, okay? And this approach of basically taking the training examples, not all as one batch in each iteration, maybe partitioning them into batches and running through each batch, okay, will then enable us to have a lot more iterations in the given unit of time. And so when you're trying to use optimize something by gradient descent search, the game that you play to try to optimize it is basically making sure that you use the right batch size for estimating what the gradient is at any given point. We use all endpoints. It's very expensive. We use 1 point. It's very fast, but it's pretty noisy. If this example was, not representative, it might lead us in the wrong direction. Okay. But the hope is that a modest sized batch size will be representative and yet fast to compute. By playing games with the batch size and playing games with the learning rate, hopefully we can make this optimization very, very fast for convex functions. Any questions about stochastic gradient descent search? This is the idea behind many machine learning algorithms, okay, and is the key thing that makes this thing run fast. Any questions? Okay, good. Now, there's one other, let's say, idea I want to talk about here with respect to gradient descent, with respect to regression, that is important, okay? And it has to do with a problem of let's say we have a regression model on many, many different points. So, let's say you have a lot of different features. You have m different features or dimensions in your regression model, okay? Many of these dimensions are probably, or features are probably not that important to the prediction of y. Okay. Many of them may be somewhat correlated. Many of them may be, relatively unimportant. Okay. When you try to fit a regression model where you have a huge number of parameters, okay, often the model that you get back is not very interpretable because it's going to make its predictions by a little bit of effect from each one of these features. Okay, if we remember back to Occam's razor says that the best explanation is the simplest one. If you're trying to do a regression where you have a huge number of dimensions, a regression model where you only have, let's say, 5 parameters that you end up using, okay, whose error in predicting the data is almost as good as a model on all 200 parameters, this is probably a better model. It is probably more robust. Okay, when you have a larger number of the more dimensions you have, the easier it is to fit the data accurately. Okay, if you have n, let's say you want to build a linear model. Suppose you have n training examples, and each one of these was n dimensions. Okay, trying to find what is the parameter that fits all the training examples. If you have n training examples, each of which has n dimensions, n features, okay, basically there is going to be a way to fit the target values exactly, okay, but this is almost certainly overfitting. You're much better off if you could try to find a simpler way, okay, a way with less dimensions that gives you a pretty good model. One way you can deal with the problem of too many features might have been to do something like a singular value decomposition. Before, if we had n points in m dimensions, if we could come away and produce an n by k matrix that almost, kind of captured all the value of this n by m matrix. Now fitting the regression problem here is going to be a regression problem in k dimensions. Okay, so you can get away with fewer training points here. Okay, but if we don't want to reduce the feature set for our model, we would still like to be able to have a version of regression that would try to identify what the most important variables are and fit only those. Okay, any questions about that? Actually, how might you think one way to do this, actually, it's maybe worth discussing. If I have m features and I want to reduce those features down to a smaller set, what would be a way to do it, a natural way to do it, other than SVD or something like that, something more natural? If you're given a data set with, where you have a lot of columns, how do you decide which columns to throw away? Does anybody have a proposal?
I'm sorry, could you repeat that again?
Again, suppose, let's say you come to me and say, I want to predict what's going to be the winning movie. I have 200 dimensions, 200 columns, and 1,000 training points. I'd say, well, get rid of the columns that are unimportant. What would be good candidates for the columns that are unimportant? The lesson on the chat, someone says maybe one that has a low correlation, where the individual variable has a low correlation with the target that you're trying to predict. Okay. So suppose, what you call it, one of the, if one of the variables was very unimportant, okay, it would presumably have a low correlation with what you're trying to predict. And so one approach, if you want to reduce the number of variables, would be to do the correlation analysis and throw out the ones that have the lowest correlation with the target. Why does everybody see that that's not a bad idea? At least originally, that seems like a reasonable start. Why might we want to throw out variables, though, that have a high correlation with the target? Anybody think of, suppose I have a variable that has a relatively high correlation with the target. Is there any reason why I might want to throw that one out?
Well, if we mentioned earlier, if it's too high, then it might just be modeling the same thing, kind of like height in feet and height in meters.
Well, okay, if I have feet in height in feet and height in meters, both of them would have an equally strong correlation with a target, let's say to predict weight. I wouldn't want to throw both of them out, but I might want to throw one of them out, okay? So if the variables are highly correlated, I wouldn't want to keep only the I wouldn't want to keep only the highest correlated features if those features are highly correlated among themselves, okay? That was the kind of thing that would be picked up by SVD, okay? But in general, we could do feature selection by using our wits to say what columns don't matter, or by throwing out the columns with the lowest correlation, and maybe keeping an eye on which columns among themselves have a high, if we did the, what do we call it? The autocorrelation function. If we computed the autocorrelation function of the variables, making sure that if two variables have a very high correlation between them, okay, throw out, make sure I don't keep too many copies of that. But ideally, we would be able to have an algorithm that will tell us which features are not important, okay? And we would like it to be the case that when our regression, our linear regression thing is trying to find the best fitting line, we would want it to try to keep Occam's razor in mind. Right now, all it's trying to do is to minimize error, but maybe by picking a different objective function, we can get a model that is more satisfying to us. So the idea of regularization is an important idea here. Okay, before, this was the least squared errors term in that we were using for linear regression. Okay, this was the penalty that we should get because we're not fitting the the points very, very well. What if we add another expression to our let's say our loss function? They call this error function people sometimes call a loss function. Okay, what if we add a function which is summing up over all the parameters in our space? Okay, here the coefficients of our line, the number of dimensions. What if we sum up, give you the sum of, we sum up the squares of each coefficient, and we add lambda times the sum of the squares of the coefficients to our loss function. Now, when we try to find what are the values of the parameters that minimize our loss function, we want it to fit the points well. We also want what? We also want, how do we keep the sum of the squares of the coefficients small? If this is the error and we want to minimize the error, how does the model, okay, keep the sum of the squares of the coefficients low, Well, it's going to pick small coefficients. If we have an error function that is the fitting error plus lambda times the sum of squares of the coefficients, the goal is going to be to make sure that the absolute value of our coefficients is small. Okay? And so trying to find the parameter that optimizes this, okay, we would get a line that does a pretty good job of fitting the points, but does so with low values of coordinates. Okay? And this is probably a more satisfying model. You know, I have seen regression things where, you know, let's say you could imagine where when you fit this line, it comes out to be something like minus 1 million plus, you know, 1.001 million x. Okay? If the parameters here are very big, you could sometimes imagine that the best fit. I mean, let's say we have two highly correlated variables, okay, and they go highly anti-correlated variables. Maybe we would end up with a fit that looks something like, you know, again, minus 1 million times x plus 1 plus 1,000,001 times x2. Okay, these models are kind of unsatisfying because, you know, it doesn't tell us very much. These weights are kind of offsetting each other. Under a, you know, what you call it, if we had a regularization to minimize the sum of the squares of these things, the model would be much happier with something like x1 plus, you know, minus x1 plus x2. And that should yield almost the same result. Any questions about that? Okay. Does everybody see that this model, okay, if we try to minimize the error, what we're going to end up doing is we're going to try to fit the points well while minimizing, but while keeping the coefficients small. If we keep the coefficients so small that the lambda is that sigma, the weight for that coefficient, the coefficient for that variable is 0, that is the same as eliminating that variable from the model. Okay? So with a regularization like this, we get smaller coefficients, which are more interpretable and kind of aesthetically more likely to be right. And if we get lucky, we will have coefficients at 0 or near 0. And that's dropping variables from the model entirely. Any questions? Okay. So again, if we think of a world, again, as far as how to think about these coefficients, if the variables we had were turned into z-scores before it, the mean value of the each variable of each dimension was 0. Then the coefficient will be able to, if it's a positive coefficient, it tells us that that variable is positively correlated with the target. If the coefficient is negative, we know that it's negatively correlated with it. And it gives us a way of modeling these things. So that's one way to interpret what the coefficients are. The sign tells us whether it's helpful or it's positively or negatively correlated with the target. The magnitude tells us something about how important it is if all the variables have been properly normalized. Okay? When we minimize the sum of the squared coefficients, that's what we call ridge regression. Another metric that you can use is, instead of trying to minimize the sum of squared of the coefficients, you might try to minimize the absolute value of the coefficient. Okay? So not squaring it, but absolute thing. That's another regularization condition called lasso. Okay. Any questions about that? What is the effect of this lambda parameter? I have a lambda parameter here. What is the value of that lambda parameter in terms of this regularization? Any ideas?
Well, isn't that just kind of like the learning rate from before? Or you could just tweak
Okay,
it?
so lambda you thought was a learning rate. Learning rate was on step size. That was applied to the derivative. This is in the error function itself.
Well,
What
yeah,
does that lambda tell you? Okay,
it's it's a hyperparameter that makes you select for it's like setting an epsilon for which coefficients you want in each one's you
it's
don't.
a question. It's an epsilon. Okay, it is a hyperparameter is the right way to I would put it. The trade-off: how much do we value a good fit to the points versus how much do we value a simple model? If we set lambda equal to 1, okay, actually, or lambda equal to a very large number, the model will be very happy to return to us a best fitting line with all the coordinates equal to 0. If we set lambda equal to 0, it will return us a model that purely tries to minimize the sum of squared error of the fit. Larger values of lambda it means higher regularization, means it increases the amount that you value the simplicity of the model. Okay, any questions about that? So this is the thing that you would play with to decide whether, how much you value the regularization. Any question? And again, how do you set I guess that's basically what I just said. Okay. How do we set what that lambda is? Okay. Well, how would you know whether a lambda was good or bad for your particular problem? Okay. Let's think about it from a thing. It should be clear to you that you could clearly add these regularization terms, okay? And the optimization will do regularization. What is the effect of changing this lambda? Okay? It should be the case that if we come up with the least squared error, this is the, what I will call the, least squared error. As lambda is 0 is where it will, on the training, lambda equals 0 would be where, if this was lambda, would be where you would minimize the fitting error on your training set. As lambda increases, okay, you'll get more and more fitting error. This is going to be a convex kind of thing, okay, because you can only increase your fitting error when you try to optimize it where you're valuing something else. Hopefully, when you use different values of lambda, there is a range of lambdas where increasing the amount of regularization, meaning shrinking the coefficients, has very little, doesn't make the least squared error that much worse. Okay? Then presumably, if you use too much regularization, the quality of the fit of your training example at some point becomes unsatisfying. Okay? We would expect that this red thing, if this is the fitting error, as lambda gets higher, there's more fitting error. However, if we're lucky, what should the evaluation error be? Remember, when you did your machine learning, you broke your examples up into a training set and a test set, right? What would we hope is going to happen if we now plot the test error as a function of lambda? Hopefully, it's going to look something like this. Okay? If it looks something like this, this means that once you get to a certain lambda, here is where, okay, again, for small error lambda, it's going to have a tendency to overfit the training example. As you simplify the model, it will do a less good job fitting the training data, but the hope is that the result is will generalize better to your test data. Okay? If you have a curve like this, we're kind of hoping the best value of lambda would be the one that minimizes the test error. Any questions? So in general, we have a world where we have a trade-off. Again, a good fit, okay, with small number of parameters is generally more robust than a slightly better fit with many parameters. And so one way to do this, like I'd say, would be that you evaluate the test error and not just the training error. When you do it with a bunch of different what you look for the minima of the test error, not just the training error. Okay. There also are in machine learning various criteria people have defined to evaluate a model as a function of not only its error, here L is a function of the error, okay, and a function here K is a function of the parameter count. So one idea would be you use one of these criteria people have defined, and you try different models and you select the one that has the best value of this. The other that I like better would be you look at the test error, okay, and you see where the test error is minimized. Any questions? The final thing that I guess I'd like to say is incorporating regularization into this gradient descent search way of minimizing the optimizing for the model. Okay, it seems clear to me. It's easy to see for me to see how you add that to the how you can incorporate regularization in gradient descent search in the parameter searching way of identifying models. It's less obvious how you can incorporate that into the linear algebra, okay, method. In fact, there are linear algebra formulations that will enable you to find the optimal coefficients with regularization, okay, by again taking this thing and building the right matrix and and then inverting it, okay. But bottom line is I find that I like the gradient descent like way of thinking about this, in terms of explicitly minimizing the error by searching in parameter space. And this is the way it is typically done in any fast linear regression solver these days. Any questions about that? Any questions about regularization or gradient descent search or anything like that? Okay. Okay. If not, that's where I'm going to end up today. If you want to talk about your projects, I'm happy to say get on. I'll talk to people quickly after the call here, or get on into my office hours, which is where I'm going to go right after this. Any other questions about linear regression or regularization? If not, thanks for your attention, and I will see you guys next time. Okay, bye.